So for this homework, what we need to do is to derive the thermodynamic factor matrix starting from equation 1.30 and explain how it leads to equation 1.32. So now let's take a look at equation 1.30. So for a non-ideal multi-component mixture, the driving force of species I equal to molar fraction of I over RT, in which R is gas constant times T is temperature times gradient times chemical potential of I. The subscript T and P are to emphasize that the system is at constant temperature and pressure. So this would be equal to xi over RT, and now I'm gonna rewrite the gradient as d over dz. So gradient is basically the derivative with respect to position. I'm using z for position because we already used x and y for molar fraction. So using z for position just help to reduce any unnecessary confusion later. Then times with mu I. Mu of I is chemical potential of component I, which is defined as changes in give free energy with respect to moles of I at constant temperature and pressure, which is equal to chemical potential of I at standard state plus gas constant times temperature times natural log of activity coefficient of I times mole fraction of I. One thing to keep in mind is that activity coefficient of I is dependent on molar fraction, and molar fraction is dependent on position. So it's basically say activity coefficient of a species is a function of molar fraction, and molar fraction is a function of position. We're gonna need to use it later. So now I'm gonna substitute this into the equation. So we have the driving force equal to molar fraction of I over gas constant times temperature times derivative with respect to position of chemical potential of I at standard state plus gas constant times temperature times natural log of activity coefficient of I times molar fraction of I. So because chemical potential of I at standard state is not dependent on position, so this is going to be 0. So we have xi over RT times d over dz RT times ln gamma I xi. Then RT and RT cancelled out, which leaves us molar fraction of I times derivative with respect to position of natural log of activity coefficient of I times molar fraction of I. To calculate this derivative, we will need to use chain rule. So we have driving force of I equal to molar fraction of I times 1 over activity coefficient of I times molar fraction of I times derivative with respect to position of activity coefficient of I times molar component of I. Xi and xi cancel out, so it equal to 1 over activity coefficient of I times derivative with respect to position of activity coefficient of I times molar fraction of I. Then to calculate this derivative, we need to use product rule. Therefore, driving force of I would be equal to 1 over activity coefficient of I times activity coefficient of I times derivative with respect to position of molar fraction of I times molar fraction of I times derivative with respect to position of activity coefficient of I. Next, I will open the parenthesis. So we have di equal to dxi over dz plus xi over gamma I times d gamma I over dz. So from equation 1.30, we have this. So now let's take a look at this derivative. This is the derivative with respect to position of natural log of activity coefficient of I. Using chain rule, we would have that equal to 1 over activity coefficient of I times derivative of activity coefficient of I with respect to position. So we basically have this equal to this. Therefore, we can rewrite the equation as di equal to dxi over dz plus xi times d over dz of ln gamma I. Okay, so as I mentioned before, the activity coefficient of a component is dependent on molar fraction of the component, and their molar fraction is dependent on position. Therefore, I can rewrite that equation as driving force equal to derivative of molar fraction of I with respect to z plus molar fraction of I times partial derivative of natural log of activity coefficient of I with respect to molecular fraction of species 1 times derivative of molar fraction of species 1 with respect to position. We will do the same thing for species 2, which is partial derivative of ln gamma I over dx2 times dx2 over dz. And similarly, we have the third element. So now let's say I equal to 1. Then we have the driving force of species 1 would be the derivative of molar fraction of species 1 with respect to position plus molar fraction of species 1 times partial derivative of natural log of activity coefficient of species 1 with respect to molar fraction of species 1 times derivative of molar fraction of species 1 with respect to position. So what I'm doing is basically substituting I with 1. The next step, I will group these two together. So we have derivative of x1 with respect to position times 1 plus whatever left here is x1 times partial derivative of natural log of activity coefficient of species 1 with respect to molar fraction of species 1. Then I will make this have the same form as this. So it'll be dx2 over dz, open parenthesis, because we don't have anything here, so it'll be 0, plus whatever left in here is x1, partial derivative of natural log of activity coefficient of the first component with respect to the molar fraction of the second species. Similarly, we have that for the third component too. Etc. Using the same method, we can calculate the driving force when I equal to 2, 3, 4 until n. So seeing the pattern of the equation, I can rewrite the equation as a shorter form. I can rewrite the equation in a shorter form as the driving force of I would be equal to the summation of delta ij, I will define it later, plus xi times partial derivative of natural log of activity coefficient of species I with respect to molar fraction of species j when j go from 1 to n minus 1 times derivative of molar fraction of species j with respect to position. And delta ij is called Kronecker delta. The Kronecker delta ij, would have a value of 1 when I equal to j, and it'll be 0 when I and j are not equal. So this is this. And we call this part thermodynamic factor of between I and j. Then this part, as we talked about it before, it is gradient. So I can basically rewrite that equation as driving force of species I equal to the thermodynamic factor matrix times gradient times molar fraction of species I at constant temperature pressure. So this is equation 1.32. So from equation 1.30, I have explained how I got the activity coefficient, how I got the thermodynamic factor matrix and how it leads to equation 1.32. So for further clarification, let's say I have a mixture of 3 components. So the thermodynamic factor of this mixture would be, so for the first row, I would be 1, and first row I would be 1. The first column, j would be 1. And then next, j would be 2. And then j would be 3. So now we're gonna substitute this into the equation that we have here. So when I equal to j equal to 1, the delta ij would be 1 plus x1 times partial derivative of ln gamma 1 over dx1. So j equal to 2, I equal to 1. They're not the same, so delta ij would be 0. And we would have this equal to x1, because it's on the first row, and I equal to 1. Partial derivative of activity coefficient of 1 over dx2. And similarly, we have the third item. Next, the second row. In the second row, I value would be 2. And then because I is 2 and j is 1, the delta would be 0. So right here we would have x2 times partial derivative of natural log of activity coefficient of species 2 with respect to molar fraction of species 1. Then next we have I equal to 2, j equal to 2, so we have 1 plus x2 dln gamma 2 over dx2. Similarly, we will have the last item on the second row as x2 dln gamma 2 over dx3. And then we will do the same thing, and the last row's value would be x3 ln gamma 3 x1, and then x3 dln gamma 3 over dx3, dx2, and 1 plus x3 partial derivative of natural log of activity coefficient of species 3 with respect to molar fraction of species 3. So this is an example of the thermodynamic factor matrix for a mixture of 3 components.